Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss evaluation of definite integrals by using residue theorem. Some kind of definite integrals, when we evaluate, it is more tedious by general method, but when we apply residue theorem for calculating that particular definite integrals, it is too easy to find out the solution of that kind of definite integrals. So, here we have three different kinds of definite integrals, and we analyze how to evaluate this type of definite integrals by using residue theorem. Type 1, integration around unit circle, when the type is given as integration from 0 to 2 pi, that function is in the trigonometric form sin and cos of d theta, where f of cos theta and sin theta is the rational function of cos theta and sin theta. How we solve that kind of definite integral by using residue theorem? First, we convert sin theta and cos theta into z, and we prefer the contour integration as taking a unit circle of radius 1. So, sin theta is written as e to the power I theta minus e to the power minus I theta divided by 2i. So, let putting z is equal to r into e to the power I theta, as we take the unit circle. So, radius will be 1 into e to the power I theta. Sin theta in terms of z is written as 1 divided by 2i z minus 1 by z. Again cos theta written in terms of z, cos theta is equal to e to the power I theta plus e to the power minus I theta divided by 2, which is equal to half z plus 1 by z. Z is equal to e to the power I theta, differentiating. So, dz is equal to e to the power I theta I d theta. So, z is dz is equal to z I d theta. So, d theta is equal to dz by I z, and its limit from 0 to 2 pi. When theta is equal to 0, then z also 0. When theta is equal to 2 pi, z also 2 pi. Limit also varies from 0 to 2 pi. In this way, that particular integral now converted into the function of z, and by applying the Cauchy's residue theorem, we can easily evaluate that kind of definite integrals. Let me prefer a problem as an example. Evaluate the integral given as that integral from 0 to 2 pi d theta divided by 5 minus 3 cos theta, that is in the form of cos theta. We can apply Cauchy's residue theorem to evaluate that kind of definite integrals. So, solution: (0 to 2 pi d theta divided by 5 minus 3 cos theta, which is equal to 0 to 2 pi d theta divided by 5 minus 3. In place of cos theta, we substitute e to the power I theta plus e to the power minus I theta divided by 2. Let me put e to the power I theta is equal to z. Let put e to the power I theta is equal to z, which implies dz will be I e to the power I theta d theta. From that we have d theta is equal to dz divided by I z, dz divided by I into z. That integral now converted to integration over 0 to 2 pi. In that of numerator denominator side 2 as LCM, that 2 to the numerator side, your 2 d theta divided by 10 minus 3 e to the power I theta minus 3 e to the power minus I theta. Now that integral converted to the contour integration over C, 2 divided by 10 minus 3z minus 3 by z in place of d theta, that is dz divided by iz. As we prefer the contour integration, x o x dash y o y dash, it has a unit radius, so the contour C is drawn. Where C is the unit circle where magnitude of z is equal to 1. Again, that integral is simplified as z is multiplied within that bracket terms, so minus 2 by I to the outside, closed curve integration over C, dz divided by 3z square minus 10z that is when z is multiplied, so we have minus 3z square plus 10z plus 3, it is minus 3. Just I am wrong with rearranging that one, so therefore I just adjust it. Now here I just multiply I on numerator and denominator, there will be no such change, that expression will be changed to 2I, as I square is equal to minus 1 minus plus, so 2I integration over C dz written like here minus when taken as common, here the terms are written as plus 3z square minus 10z plus 3. The expressions are written as 3z square minus 10z plus 3. Let I take that integral as I. Let C dz divided by 3z square minus 10z plus 3 is equal to I. To solve that contour integration, first we have to evaluate what be the poles of that particular integral. Poles of the integral, poles of the integral equate the denominator 3z square minus 10z plus 3 is equal to 0. From the product we have multiplying two numbers results 9, adding two numbers results minus 10. So that number will be minus 9 and minus 1 is written as 3z square minus 9z minus z plus 3 is equal to 0, which implies 3z as common. We have z minus 3 plus minus 1 taken as common, z minus 3 is equal to 0, which implies z minus 3 whole into 3z minus 1 is equal to 0, which implies z minus 3 is equal to 0 or 3z minus 1 is equal to 0, which implies z is equal to 3 or z is equal to 1 by 3. Therefore, z is equal to 3 and 1 by 3 are the poles. These two are the simple poles in that of figure. Here 1, 2, 3, 3 that is the outside of the circle, 1 by 3 which is within that of contour. So at that given pole 1 by 3 we can easily calculate the residue. There is only one pole at z is equal to 1 by 3 which is inside the unit circle C. Therefore, residue at z is equal to 1 by 3. That is the simple pole. So residue is evaluated limit z tends to 1 by 3 z minus 1 by 3 of that given function f of z, limit evaluation limit z tends to 1 by 3 z minus 1 by 3. In that of f of z we have 1 divided by that function, that is written as that form z minus 3 whole into 3z minus 1. In 3z minus 1 we can take common as 3, limit z tends to 1 by 3 z minus 1 by 3 1 divided by z minus 3. Here 3 as common, we have z minus 1 by 3 z minus 1 by 3 z minus 1 by 3 cancel out. Now evaluating the limit at z tends to 1 by 3, we have the limit evaluation the limit evaluation 1 divided by 3 whole into 1 by 3 minus 3, (1 minus 9 by 3). Three cancel out, minus 1 by 8. The residues at that given point is calculated. Okay. Now we have to use Cauchy's residue theorem. Hence, by using Cauchy's residue theorem, I is equal to 2 pi I into sum of the residues within that contour, sum of the residues within contour, which is equal to 2 pi I into minus 1 by 8, minus 1 by 8. The result will be minus pi I by 4, minus pi I by 4. Therefore, the result 0 to 2 pi, the given integral d theta divided by 5 minus 3 cos theta. How we have to evaluate that one? That is the 2i into I, 2i into the given integral I, results 2i into minus pi I by 4. I square is equal to minus 1, minus minus plus, the result will be pi by 2. The result will be pi by 2. So, here the type 1 integral in the form of cos theta and sin theta under that of unit circle, at the evaluation procedure, an example how we have to solve that kind of definite integral by using residue theorem. Type 2, evaluation of minus infinity to plus infinity f1x divided by f2x dx, where f1x and f2x are the polynomials in x. Such type of integrals can be reduced to contour integrals. The condition will be f2x has no real roots and the degree of f2x is greater than that of f1x, at least 2. Then that type of integral can be converted into contour integral, and by using Cauchy's residue theorem we can solve that type of contour integral. So, the procedure how to solve that kind of contour integration, let we prefer that function f of x is equal to f1x divided by f2x, and consider the contour integration over c f of z dz, where c is a curve that consisting of upper half CR of the circle z is equal to r. We draw a circle having the radius as r, the upper half consider as CR, which is arbitrary, can be taken such that there is no singularity on its circumference CR in the upper half of the plane. On that of upper half there will be no such singular points on that of CR, but possible some poles inside the contour C, but there will be some poles within that of contour C. At that of case we use the Cauchy's residue theorem. The closed curve integration over C f of z dz is equal to 2 pi I into sum of the residues f of z at poles within that of curve C. In that of particular contour, we say that closed curve integration of that of given function, that from minus r to plus r, and again at CR minus r to plus r f of x minus r to plus r f of x dx, and inside that of contour f of z dz CR is equal to 2 pi I into sum of the residues within that of curve C. minus r to plus r f of x dx is equal to minus of, when that integral to this side, so minus of cr f of z dz plus 2 pi I sum of the residues within that of c, taking the limit as r tends to infinity. Here taking the limits r tends to infinity, we have here the limit is taken within that bracket term. So, that limit when we evaluate f of z dz r tends to infinity cr, in place of z we substitute r into e to the power I theta, whereas dz is equal to r e to the power I theta I d theta. In this way d theta is evaluated. D theta is equal to r e to the power I theta dz divided by I. By putting all these values, as we calculated the limit from 0 to 0 to pi in that of semicircle, that theta varies from 0 to pi, therefore the result will be 0. So, that integral vanishes. So, we have that limits from that of real factor from minus infinity to plus infinity. So, minus infinity to plus infinity f of x dx is equal to 2 pi I sum of the residues within that of closed curve C, within that of contour C. In this way, that kind of definite integrals can be solved by approaching the semicircular contour. Let us refer an example which satisfy in the form of type 2. Example, evaluate the integration from 0 to infinity cos mx divided by x square plus 1 dx. Let us solve that one. Solution: consider the integral f of z dz, where f of z is equal to e to the power I mz divided by z square plus 1. Cos mx can be written as e to the power I mz. We only consider the real parts that taken round the closed curve closed contour C, that is consists of upper half of a large circle magnitude of z is equal to capital R, and real axis from minus r to plus r. Draw that of semicircle. X O x dash, y O y dash, from plus r to minus r inside that of real axis. This is CR. look at that function in that of numerator, in that of denominator we have z square plus 1. When equate to 0, we have the poles of that given function. The poles of f of z are given by z square plus 1 is equal to 0, which implies z square is equal to minus 1, which implies z is equal to plus minus under root of minus 1, which implies z is equal to plus minus I. In that of contour, as we consider only the upper half, so plus I within that of contour, minus I is not within that of contour. So the only pole which lies within the contour as at z is equal to plus I, and we evaluate the residues at plus I. Therefore, the residues of that given function f of z at z is equal to I. It is a simple pole, so residue is evaluated as limit z tends to I, z minus I given function e to the power I m z divided by z square plus 1, z square plus 1 is equal to limit z tends to I, z minus I e to the power I m z divided by z square plus 1 can be written like z plus I whole into z minus I, z minus I, z minus I cancel out. So the limit is evaluated by putting z is equal to I. So we have the limit as limit z tends to I e to the power I m z divided by z plus I, evaluating that limit e to the power minus m as I square is equal to minus 1 divided by 2I. Next, the contour integral. Hence, by using Cauchy's residue theorem, we have contour integration of C f of z dz is equal to 2 pi I into sum of the residues within the contour, sum of the residues within that of contour, which implies the contour integration that given function e to the power I m z divided by z square plus 1 dz is equal to 2 pi I sum of the residues, that is e to the power minus m divided by 2I. So 2y cancel out, we have e to the power minus m pi e to the power minus m, which implies C e to the power I m z divided by z square plus 1 dz is equal to pi to e to the power minus m. Let we choose that closed curve integration from minus r to plus r when we take the real axis. Therefore, the closed integration changes to minus r to plus r e to the power I mx divided by x square plus 1 dx is equal to pi e to the power minus m. Equating the real parts, we have minus infinity to plus infinity e to the power minus e to the power I mx. The real part will be cos mx divided by x square plus 1 dx is equal to pi e to the power minus m. But our requirement is that integral from 0 to infinity. When the limit changes from 0 to infinity, cos mx divided by x square plus 1 dx, we have the result as pi e to the power minus m divided by 2. Here 2 times of 0 to infinity, 2 is divided here, that is the answer. By using the contour integration, we can solve that kind of definite integral very easy way. That is basically for type 2. This is a procedure how we evaluate that kind of definite integral by using Cauchy's residue theorem, and an example to solve that kind of definite integral. Another type 3, intended semicircular contour, when the integrand has a simple pole on real axis and it is deleted from the region by intending that particular contour, which is a small semicircle having the pole. That pole is drawn in that of semicircle. Now, by taking an example, we can easily explain type 3 definite integrals. By contour integration, prove that from 0 to infinity sin mx divided by x dx, which is equal to pi by 2. Solution: consider the integral contour integration e to the power I mz divided by z dz, where we choose C is a large semicircle having magnitude of z is equal to r, but that is intended at z is equal to 0, that is one of the pole. From that expression it is clearly understood. Let me take small r be the radius of that indentation taking the real axis as x, o x dash, y o y dash, that from plus r to minus r. Here is the semicircle, but at that of case here the portion having the radius small r, that from plus r to minus small r. That circle is named as CR, that circle is C of small r, and it has the radius capital R. There is no singularity, there is no singularity within the given contour. The given contour just like this. Within that of given contour there will be no such singularity. The singularity is only at z is equal to 0, which is at pole, but that z is equal to 0 not within that of contour. Hence we can easily use the Cauchy's theorem. Hence by Cauchy's residue theorem, Cauchy's theorem, Cauchy's integral theorem, the closed curve integration over C e to the power I m z divided by z dz is equal to 0. That is, the closed curve is from minus r to minus r, and on that of contour CR, then plus r to plus r, again that of contour CR. So the integral from minus capital R to minus r here in the real axis, so it will be e to the power I mx divided by x dx plus contour CR, that is e to the power I mz divided by z dz plus r to plus r, plus r to plus r, e to the power I mx divided by x dx plus again CR, integration over CR, e to the power I mz divided by z dz is equal to 0. That equation number 1. Let us substituting minus x to plus x in the first integral and combining it with the third integral, we get substitute from minus x to plus x, and that integral combined with this integral minus r to plus minus r, plus r to plus r. These two integrals are combined and we change minus x to plus x in that of real axis term. We have the combination of these integrals are minus r to r, combining these two, one as e to the power I mx minus e to the power minus I mx divided by x dx plus, let us here we prefer contour C to e to the power I mz divided by z dz plus, that is, let contour C1 e to the power I mz divided by z dz is equal to 0. Let me put z is equal to r e to the power I theta, which implies dz is equal to r I e to the power I theta d theta. So its substitution e to the power imx minus e to the power minus imx divided by 2i is equal to sin mx. So 2i r to r sin mx divided by x dx plus contour c2 e to the power I mz divided by z dz plus contour c1 e to the power I mz divided by z dz is equal to 0. That is equation number 2. Now we have to evaluate each of these integrals one by one. First, second integral. Now integration over c2 e to the power I mz divided by z dz is equal to integration over c2, that is written like 1 by z dz plus e to the power I mz minus 1 divided by z dz. There will be no such change. I just add 1 and subtract 1. On that c2, here z is equal to small r e to the power I theta. That a figure, look it here, r e to the power I theta, small r. Equation number 3. Again it is in the two integral, that one, this. Therefore integration over c2 1 by z dz is equal to, here the limit from pi to 0, limit from pi to 0. The substitutions just like r e to the power I theta I d theta divided by r e to the power I theta minus integration from 0 to pi. As I multiply a minus, then the limit change I d theta, it will be results minus I pi. Next, for that integral also integration over c2 e to the power I mz minus 1 divided by z dz magnitude, which is less than equal to m integration over c2 dz divided by magnitude of z, as we studied from Cauchy's inequality, which is as pi into m. What is capital M? Where capital M is the positive number, which is maximum value of on C2 of e to the power I mx minus 1 magnitude is equal to e to the power I m in place of x, that is r cos theta plus ir sin theta minus 1 magnitude. Clearly, here clearly, when m tends to 0, as r tends to 0, from equation 3, we have the result of that term It's minus I pi. So that integral results will be as pi m. Therefore, from equation 3, from equation 3, closed curve integration over C2 e to the power I mz divided by z dz, that one, that value is minus I pi. Here that value is pi m, but when m tends to 0, r tends to 0, that results will be 0 only due to that integral results as minus I pi. It is equation number 4. That integral is evaluated just like this and it results minus I pi. Next, integration over C1. Now again integration over C1 e to the power I mz divided by z dz. Here putting z is equal to capital R e to the power I theta, that is on curve C1, integration from 0 to pi, that is integration from 0 to pi. E to the power I m r cos theta plus I sin theta divided by r e to the power I theta into r e to the power I theta I d theta, which is equal to I to that of outside 0 to pi e to the power I m r cos theta into e to the power minus I square minus m r sin theta d theta. Since e to the power I m r cos theta magnitude less than equal to 1, therefore under that of curve C1 e to the power I mz by z dz magnitude less than equal to 0 to pi e to the power minus mr sin theta d theta, which is equal to 2 times from 0 to pi by 2, as limits change from 0 to 2 pi 0 to pi by 2, so 2 is multiplied e to the power minus mr sin theta d theta. Also sin theta by theta, next our task is to solve that integral as sin mx by x. Sin theta by theta continuously decreases from 1 to 2 by pi, it's just reciprocal. As theta increases from 0 to pi by 2, Therefore, for the value of theta in between 0 to pi by 2, sin theta by theta greater than equal to 2 by pi, or sin theta greater than equal to 2 theta by pi. Next, that magnitude term now evaluated. Therefore, the closed curve integration over C1 e to the power I mz divided by z dz magnitude is greater than equal to, sorry, less than equal to 2 times 0 to pi by 2 e to the power minus 2 mr theta by pi d theta, which is equal to minus pi by mr e to the power minus 2 mr by pi from limit 0 to pi by 2. That value will be pi divided by mr, 1 minus e to the power minus mr. As r tends to infinity, so pi by mr, 1 minus e to the power minus mr tends to 0. Therefore, the given integral e to the power I mz divided by z dz will be 0. That integral will be 0. That's why from equation 2 we show that, hence from equation 2 on taking the limits as r tends to 0 and capital R tends to infinity, we get 2I from 0 to infinity sin mx divided by x dx minus I pi is equal to 0. That integral value as minus I pi, that integral value as vanishes 0. So, the contribution only that term which is minus I pi. So, integration over 0 to pi sin mx divided by x dx is equal to pi by 2. That will be the answer of that given question, which is type 3 as intended semicircular contour. The given problem, we use Cauchy's theorem. Next, these three integrals are evaluated. First, taking C2, the result we obtain as minus I pi. Next integral over C1, the result we obtain as 0. By putting these values, finally we have the solution of given integral, which is pi by 2. So, with the help of this video lecture, we understand evaluation of definite integrals using residue theorem type 1. An example related to type 1. Type 2, and the technique to solve this type of integration, and an example based upon the type 2 and its solution. Next, type 3 and an example related to type 3 and its solution. So with this useful and informative notes, let me wind up this session. Thank you.